Okay, now we get to a very simple reactor where we define the vinyl acetate monomer process. We can see the inlet stream. Yeah, we have like a 148 degrees C, 8.8 bar with this composition. We have oxygen, CO2, ethylene, ethane, vinyl acetate, and then water, and then acetic acid. Yeah, so basically, when we go to the flow sheet again, and then what's in the reactor is, we have the specification is. So we have this reactor is then we have a constant thermal fluid temperature, so it's encapsulated within the thermal fluid, and that thermal fluid is constant at 133 degrees C, right? And then from the reactor, because it releases heat, the U value from the reactor to the fluid, it's about 150 kilocalorie per hour square meter Kelvin, basically. And then it's a tubular reactor with 622 tubes. The length is 10 meters with this 3.7 centimeters in the diameter. And then the process stream is vapor only. And then the reaction is defined in here, PR1. So we have a main reaction and then side reaction configuration. So the main reaction is then if we double put together, you can ethylene plus acetic acid plus half oxygen, we get vinyl acetate, and then water. And then if there is an excess, so it's competing reaction between the main reaction and then the side reaction. So the ethylene will be burned because of the presence of oxygen, and then the kinetic. Yeah, so this is the main reaction. So the kinetic is this guy for the collision frequency, and then this the activation energy, 7 kilocalorie per mole. And then the reference temperature for this data is 150 degrees C, and it's based on the partial pressure, vapor, and then this is then the exponent for the reactant. So we have it's in the higher order of 1 for ethylene, and then 0.01 for acetic acid, and then 0.01 for oxygen. Basically, it's highly dependent on the ethylene. So that's the main reaction. The side reactions is yeah, this guy. So if you can tell the so this reaction is like 10 times faster roughly than the main reaction, which is to be when the side reaction, which is to be expected, right? Otherwise we'll be having the side as the main and that way around. And then the amount of energy required is also double. So in the main reactions we have like a more than double, about 7, and then this guy is about 20. So it's more energy to get through this second reaction, basically. The setup is the same: vapor, partial pressure, and then ethylene and oxygen in the exponent. And then we create also activity. You will see why we created this later. By activity, and then this is something that we want to like tune in a way later on. So we specify activity A and with a value of 1, and then we use this in the main side, in the main reaction, not on the side reaction, but the main reaction, meaning that the side will happen as we define it, but then the main we will then change it later accordingly. Okay. So this numbers where's the reaction again? Yeah, so again 133 thermal fluid, and then the U is 150, and then the reaction is 1, and then pressure is this number. I can put this pressure the same, basically the stream pressure drop to 0.6. There's no hold up, and then the catalyst is bed voidage, yeah, thickness first, and then bed voidage of 0.9, and that is then the density, quite double the density of water, basically. And then if we run this, I think I've run this. and then we can see the results. Right, so we have a heat duty, right, so it's releasing the heat, and then profile, and then you can see here the temperature. So you can click this and then get the plot against the temperature. The stream is a reactor length, and then yeah, so we are using the x-axis as the reactor length with the length of the unit of meter. Click OK, and then you could see it is a temperature along the length of the reactor, 10 meters, right? And then the inlet temperature, and then 1 meter after the inlet, 2 meters, and so on and so forth. And then it has the maximum temperature around 6 meters in the reactor, which is around 160 something, right? So as we have more reactions happening, and then with a constant 133 degrees C of cooling medium basically, and then 150 U, we get this profile. You could run and then test a different cooling medium temperature and also the U, and then you will get a different profile. So this is basically how we set up the simulation. And then if we happen to be like in the we change it to equation oriented, and then in the simulation as well, equation and the simulation, and then we run it, right? So all this is like a more granular somehow, and then we can see in the we can see of course in the EO variables, in the EO configurations. Once we see that, we will see all of these variables, right, with the specification of constant, and then if we double click, we get reconciled constant, and then we double click again, we get the calculated. So that's how we go through it. And then if you want to see what the reactor temperature is, so we can create like right click and then add new, and then which I added already, and then we can then query. So because what I want to see is only the temperature profile from 0 until 10, and then the U value that we put in, right, which is then constant. As you can see, it's a constant because we put in the U value, and then this is then the reactor, the cooling medium, which is 133, which is a constant. That's what we put in, and then this is then the activity that we just key in. This is like it's going to be put reconcile. Previously it's a constant as well because we put it constant, but now because since I'm running the already existing simulation, this is why we put it in the spec group. In the spec group, we create a new group, and then in the group we call that variable here, and then we say it's reconcile, meaning that we will then be using this later in the data reconciliation mode. But now since we are running only in the simulation mode, this guy is not being used anyway. So the value is 1, and then as you can see here, the value is that guy. The value is 1, right? So now if we to reconcile this, we then need to make what is then the basis for reconciliation, right? So in our case, we have the temperature measurement along the reactor, so which may be different than the calculated values over here. So we put that in the EO input. In the EO input, sorry, not the EO input. We put like a measurement in here. So that's why we have this measurement in it. So we can just simply either put the manipulators, this measurement, on the flow sheet, or just create new, and then you will get this guy. So in this input, we create a tag 1 until 10, and then so temperature as well, and then this is the plant value, right? Plant value, which is different than the that guy again. Temperature plot. Now we just put temperature plot over here. My temperature file. Right. So this number is then the calculated number, while the there are so many windows, while the The one in the measurements is then the plant data, assuming that we get it from somewhere. And unit C and then offset value is 0, and then we say this then the values, right? But first we have to make the connections basically. So make the connections, create a tag, and then this tag is connected to this variable in the reactor, right? And then the way you can find it is simply click on it and then you can find it. So this tag connected to this variable, and so on and so forth. Once you get the connections, and then you then specify the value for the tags. This is the guy. And you want to say, well, we want to calculate the offset, the difference between the plant value and the input and the model value. So once we do these measurements, we put the measurements. So that means we have the measurements for temperature profile along the reactor. And then we then define the objective function. Okay, so go to the objective functions, and then we create the name like data reconciliation, so dr, how it looks like. So using the same term, same tags, and then we find this in the variable. So if you click on this, and then you can see we want to then minimize the offset, right? And we can see in the M1, which is then the measurements, because this is the offset of the measurement, you can see that this is then the offset, and then it's related to this term. So we add this there, and for each of this term we have their own offset. And then for the offset, we want to have the offset close to 0, and then standard deviation of 1, and then delta T, and then delta C, basically for the physical type and unit. And then set to minimize, and then yeah, you can make comment or whatnot. So the sum of this, so when you create this objective function, you create this, and then you will then be asked on which type. Sum of squares then the one that we use typically for the data reconciliations, because then we get the offset and then we square it, because then it's to minimize the negative so that they don't cancel out each other. So once we square it, and then we then once we sum it, and then we put it into the root, right? And then this linear is then for the objective functions, which we will I'll show you later. Now, so once the objective function is done, the offset is then being calculated like 38 degrees C, right, with the current situations. And then we change this simulation to reconciliation, and then the objective function is then the dr. Okay, and how do we reconcile this? Again, as I hinted previously, so we have what we call like the activation, right? So we want to modify the activations of the main reactions in such a way that it will then match the whole temperature profile. So it goes into the EO input. This is then the activation reactions, which is 1, and then I will just put it here so that we know this is 150 and 133. This is the ones that we are using as constant, right? So once we reconcile this, once we define what we can tune in such a way to minimize the reconciliation objective functions, we can simply go to where's my EO variables. Right, and then we can then run this so that we can see. Yeah, click OK. You can see now this is then the new calculated value for the reactor temperature. I don't remember how big the other one is. 151.4, and this is then 151.2. Right, so it's closer. And then the optimum so-called activity for the main reaction is then 0.894 instead of 1, right? And then we can see also the results in the DR. So this then the initial value is then 38.7, so that's the whole offset. And then now the offset is then only like 0.059, so which is very close to the actual plant value. And in the term results, you can see the activity as well. Oh, sorry, the temperature, say the offset. So all these are very low offset already. So the planned value, now the calculated value matches very well with the planned value. Okay, we will do the object optimization in the next video. So I think this is enough for the data reconciliation example.